Some people also like to call this structured data. And there are many reasons to do supervised learning on tabular data because it's very common in practice. Like medical data, you can have surrogate models, you can have energy forecasting if you put the forecasting aspect into it, which I won't do, or other stuff. It's also a classic type of data, both in general machine learning and also in AutoML, because you have relatively fast methods, so you actually have the time to tune them. There's also a lot of different methods, so you can do model selection. You have a lot of different data sets, so there's not just your one image net and everyone knows what's the best method on it anyway. Tabular machine learning methods are also used in AutoML, as we saw, because what we do in Bayesian optimization, if we have a surrogate, we need a surrogate. That is tabular. How do we represent tabular data? There are two popular libraries. The most popular one is pandas, and in pandas there are data frames, and you can say you have columns with these titles and these values, and then it gives you this data frame, and each column can have a different type. And data frames are what I should have learned about earlier when I started working on tabular data, or one of the things, because I should have immediately stored all my data sets in data frames instead of NumPy arrays. And also what I learned later is that data frames are also a good way to store and process benchmark results instead of nested lists and dictionaries of results. If we go back to 2022, some of my colleagues or former colleagues from INRIA Saclay, they did a benchmark on tabular machine learning models, and they found that the best model in their study was XGBoost, and in general these type of methods are all based on decision trees compared to these, which are like transformers, and these are more classical neural network methods. And you can see here the time spent on random search. And these methods are like slower per iteration, but they also max out at a worse result. So what are these methods like XGBoost? So in generally, the most popular methods on tabular data in the last 10 years are gradient boosted decision trees. So they learn a sum of decision trees or an ensemble. And in contrast to random forest, they do it sequentially. They optimize like a second order or first order approximation of the loss function. These are some of the most popular libraries. XGBoost, I think, is the most popular of the three, but of course in scikit-learn you also have one which is similar to LightGBM, and CatBoost is a bit newer. It's very good for categoricals and wins on many of the benchmarks. The neutral ones, at least. So why do gradient boosted trees work so well? This was also studied in this benchmark, and one of the reasons is because you have heterogeneous features, not all of the features are equally important. And some might be entirely irrelevant, as we already heard, and that's why random search sort of works. Because each tree construction is greedy, like you choose the feature that most improves your immediate gain. Boosted trees focus a lot on the most important features, whereas neural nets, you have the gradients, and the gradient takes a bit of each feature in each step. Then they learn axis-aligned functions because they split on individual variables. And this paper also did some experiments to show that there is actually axis-aligned information in the data sets. If you rotate them, you make boosted trees worse. Then one aspect is the ability to learn non-smooth functions. But also what is a bit conflated maybe in this experiment is that boosted trees learn an ensemble, and ensemble methods are very good in terms of their like variance. So they deal well with noisy data. Still, we want also to have neural networks. And why is that? I think there are many reasons. One is like flexibility. You don't have to go into C++ code if you want to have some custom stuff. You can add neural nets embedding methods and train them all jointly. If you have multimodal data, you can benefit from neural network research, at least if there is someone that actually tries to incorporate the research, even though you know that publishing is hard because of novelty. Yeah, smoothness, extrapolation properties, and there is plenty of research also showing that combining neural networks and boosted trees gives you huge benefits often. Now, the problem with neural nets, at least compared to boosted trees, is that they're quite slow on average. And if you need to do hyperparameter tuning, as we saw in the SMAC demo, even with small scikit-learn MLP, it can be quite annoying. So what I was looking at when designing neural networks is how to make them work well with only default parameters. And so this is here in collaboration with Leo Grinstein and Ingo Steinwarth. We looked at improving the default parameters of MLPs and also boosted trees. And how do we do it? We do it by meta-learning. So meta-learning is learning how to learn. And in meta-learning, each sample from which you learn is a data set. And so you have a meta training set, which is a whole benchmark of data sets, and you have a meta test set, which is a completely different benchmark of data sets on which you evaluate your method. Yeah, and then you can have like different levels of granularity of meta learning. Here we basically have the simplest form where you only learn a fixed set of hyperparameters for a model. But you could learn like a list of models and hyperparameters, which is called a portfolio. You could try to learn a map from dataset meta features to best hyperparameters, or you can try to learn the entire algorithm by just, yes?
Just for clarity, here you just learn static hyperparameters.
Yes.
I guess it says it in the first bullet.
Yeah. Yeah. So there's of course like the foundation models that learn the entire map from training set test point to test prediction, and of course this can only work if you have more than 100 data sets, so they use millions of synthetic data sets. Okay, there are some works that try to get along with not that many data sets, but and if you want to do this, in order to optimize the performance of your hyperparameters, you need to define how to, like, what is the scoring function that you actually optimize. For that, you need to define a base metric. So especially for classification, there are a lot of metrics. We went for classification error, but in retrospect, I would have chosen different metrics, as we will see later. And then you need some way to aggregate the results of all data sets. And here we chose the geometric mean of the errors with some offset. The offset is there because if the error is 0, it will set your whole geometric mean to 0. But I still wanted to have the geometric mean because I wanted to look at like a relative error reduction instead of an absolute reduction. And the good thing about this aggregation is it doesn't depend on which other baselines you include in your evaluation. Other things like rank, they always depend on what other methods you have. But this also has some downsides, and I could go on talking about this, but I won't. So my meta-learning approach was in some ways a bit naive. Still, I tried to use some automated methods as well. So I mean, I just have some objective function which runs one set of hyperparameters on a whole benchmark and computes this aggregated score. And so I tried some automated methods like hyperopt and SMAC. And my experiences, I was a bit disappointed that I was seemingly much better optimizing this manually than with automated methods. Maybe because I have knowledge that these methods don't have, like reading blog posts or knowing what the hyperparameters mean. But still, I use these methods because I didn't want to do the manual tuning for all combinations of boosted trees and benchmarks. Yes?
Is it okay if I ask more?
Yes.
I'm interested in the coordinate descent. Maybe also fancy because we did exactly the same. I took from figure PO.
Mm-hmm.
You also used the coordinate descent for this. I would be interested in why you did that and what the fancy part first.
The fancy part is basically remembering which coordinates did change the performance more and going back to them earlier if once. Yeah, I did that because I thought I should be able to do better, but then it's like sometimes it got stuck in a local optimum or something, but so I didn't really test it much more.
Why did you go to the coordinate descent in the first place?
Because that's what I do manually.
Yeah, you did this also first. Because it makes
Yeah.
way easier to understand what happens step by step. I guess
Yeah.
the lines a lot with
Yeah. Yeah. So for neural nets, I decided to do mostly manual experiments because, I mean, experiments take a bit of time and I wanted to get some hands-on knowledge on how it works, but still I mean, in the end, we did some ablations and like one or two of the ablations ended up showing that actually something else was better. So I guess there was some automatic tuning. Still, if I revisited it and there were some tools that had all these things like getting insights, being actually time aware because there are some hyperparameters I don't want to inflate arbitrarily, then I should have probably used such a tool because it gives me a justifiable decision and I don't have to like lose my mind a lot about deciding on the final version. Then what I think is an important aspect is just doing as many experiments as possible. So I just want to be able to run experiments as quickly as possible. And I spent quite a bit of time on optimizing the benchmarking setup. So basically, my setup was not in the beginning, but after a while, I had access to this workstation with 4 GPUs and a 32-core CPU. I noticed for boosted trees and in general, it's best to run as much processes as possible in parallel. So you just give each of them one thread and you run as much as possible in parallel. For the neural nets, the question is how do you run as much as possible in parallel? So I parallelize, of course I use all the 4 GPUs, but I notice for MLPs, it helps a lot to train multiple MLPs in parallel. I noticed already on like the old 1080 GPUs, you could train 5 MLPs in parallel without slowdown. And then I also did some experiments early on, seeing, if I have the same data set, but I do different splits into train, validation, and test. So these have the same size, the same feature dimensions, and so on. I can just, instead of training nets separately, I can all vectorize them into a net with like an extra models dimension in the parameters, and then train this one neural net. And on these experiments, I had the impression that this gives me about a 4 times speed up, so I could train around 20 neural nets in parallel without a slowdown. I didn't really benchmark that again later on. But this is a bit of a difficult choice because it makes the code really more complicated and it doesn't work in all scenarios. Also, I ended up writing my own scheduler. I didn't know that much about Slurm back then. I was on a machine without Slurm. But I think this might have some advantages as well. So I wanted to introduce it because if it's useful for someone. Of course, there is stuff like Ray, but I built this on Ray, but Ray has, I think, some problems with putting multiple processes on the same GPU and stuff like this. So basically here you can say I have my subclasses of abstract jobs. I need 10% of a GPU, and my job, I think, will need 3 gigabytes of RAM, and then you put a lot of these jobs and it will distribute all of them, run them in parallel, run the slowest jobs first, which is maybe also something that Slurm doesn't do. And it's in my PyTabKit library. I just wrote some documentation yesterday. And the annoying thing, either way how you run your jobs, is estimating the RAM usage of your methods, at least if you want to run them as parallel as possible. And so I ended up writing even more code to have some meta features and products of them and make some linear regression on top of it and fit the linear regression coefficients using some experiments. So if someone has some RAM estimation problems, there might be some opportunities to discuss that. But I mean, this occurs in AutoML tools as well, like in AutoGluon. I had some discussions with Nick from AutoGluon on how to estimate RAM for different methods. And what I noticed, so I guess a good thing about this is you don't have all the startup overhead from launching a new process, like launching a new job every time you want to run like a tiny random forest. And a disadvantage of having a scheduler within Python is some methods don't really support telling them which GPU to run on. Like I tried running AutoGluon's deep learning models, and they always run on GPU 0 if you can't tell them to run on GPU 2. So if you run jobs via Slurm, you can set an environment variable and say only this GPU is visible, and then it's much nicer. Anyway, so after all this optimization, I had this meta, for example, the meta train classification benchmark. I ran 10 splits into train, validation, and test, and it takes me around 5 minutes to run on this hardware. And with smaller neural nets, it takes even like 2 minutes. So I could just run hundreds of configurations or maybe even thousands. Yeah, we already heard about random search today. I also had a discussion with Marius on LinkedIn about this. That random search is unfortunately for benchmarking people just too convenient, at least for me. I actually started out by using hyperopts for boosted trees, and then I started using neural nets, and I was like, do I really want jobs that run for like, I don't know, 20 hours with like sequential hyperparameter optimization? And if they get interrupted, I need some saving logic that can restore my neural nets to the GPU that they are now allocated on in this new scheduler. Like, I didn't want to, so I just used random search, and then the reviewer was like, you don't use the same tuning method, so we just also used random search for the boosted trees. Yeah, and this ended up being nice because reviewers also asked for AUC results, and we just said, hey, we have random search, we can just retune the results for AUC without actually rerunning the search. And it turns out already, we will see later that instead of hyperparameter tuning, maybe you want to do weighted ensembles, and for weighted ensembles you want diverse configs to ensemble, and I don't know if you can do this with HPO tools, but you can just use random search, and so on. Yeah, so anyway, here are some results of the paper. This is, like here you can see like vanilla MLP method from 2021. Then a method that includes some numerical embedding layers that was arguably the state of the art for MLPs at the time. And then our real MLP with the meta learned default parameters on the meta test benchmark, and here for regression. And yeah, you can see real MLP always wins, but here my suspicion is that I should have optimized the search space better to to get better results. And yeah, you can see real MLP is slower, so on the x-axis it's slower, but it has a lower geometric mean error. We do outer cross-validation, but not inner, which...
You learn the hyperparameters on some tasks and then...
Yes, yes, so this is the meta test, which is disjoint from the meta train. Yeah, actually we also have the Grinstein benchmark, which is a bit overlapping, and it has some more strictly selected data sets, and their real MLP is not as good compared to boosted trees, so that is already a result in the direction of which benchmark settings influence the results. Also, we have results for other things like shifted geometric mean, and there it also gets a bit worse. So real MLP is sort of optimized to this benchmark setting as well, of course. We ended up also demonstrating that we can include some of the things in real MLP to another method and also improve it. Then we can also meta-learn better default parameters for boosted trees, but of course this is for those types of tasks, for those metrics that we meta-learned on, so it might be different for other metrics. And then, yeah, if you compare the boosted trees to MLPs, here the MLPs are much better, but as I said, on the other benchmark, it's the other way around, so it really depends, as we heard today. And what we also looked at was what happens if we, instead of tuning the hyperparameters of a single method, what happens if we tune the method but not the hyperparameters, and this is basically what we get here. If we tune the method, we get something that is like as good as tuning the hyperparameters, basically. With the caveat that this is not with inner cross-validation, so probably this overfits a bit. But yeah, in general, combining neural nets and boosted trees gives you a huge benefit compared to only having one of the two. Now, what did we do to get there? Basically, a huge bag of tricks with some new tricks and some existing tricks. So I won't explain all of these, of course, but my philosophy was to look at like all aspects of the training pipeline. Pre-processing is quite important. It improves over like just standardization. Then some of the training setup, how you train, then the architecture, of course, which is what everyone looks at. And the reviewers were like, oh, but you change things that are not the architecture, how should we interpret this? And regularization and initialization. In general, I had the impression that tuning initialization and also like things like parameterization and optimizers is a lot more frustrating and less helpful. Like sometimes it works a bit better, sometimes it works a bit worse, but like you can get more out of architecture and regularization. One thing that still bothers me with real MLP, and I don't know what is the best way to resolve it, is the time accuracy trade-off you get by early stopping. So we need to distinguish between actually interrupting the training early and training till the end, but then selecting the best checkpoint with the best validation score. So what we actually do in real MLP is we train always till the end, and then we select the best checkpoints. One reason is because we actually use a multi-cycle learning rate schedule, the blue one. The idea of that one is we don't know how long, like when the model will start overfitting, and often we want to have a low learning rates at the point where we actually select the best checkpoints. So we just do multiple cycles and take the best point, which is often in one of the valleys. Yes, but this also makes the early stopping more difficult because usually the validation loss goes up in between and then it goes down again. And so you can't just say, oh, I had the best result here and I go like 20 epochs to the right and my loss hasn't improved. Yes, but maybe it will improve at the very end. Yes?
Number of epochs or hyperparameter that you tune, or is that like fixed to a large value?
Mostly it's fixed to a large value.
And then you say by going back, you can fix.
Yes, by going back to the best checkpoint. So here in this paper we use 256. But as we saw, real MLP is a bit slower than the other MLPs, and I think the main reason for that is the lack of the actual early stopping. But I also tested a bit, and the other MLPs, they have a low patience, and if you make the patience larger, they get a bit better. So there is like no clearly best answer to how to do this early stopping in my mind. Also, we did some ablation on boosted trees, and for boosted trees, you can also do things wrong by having too low of a patience in early stopping, especially if you stop on accuracy. Like your boosted tree optimizes cross entropy loss, but so the cross entropy loss may like go down relatively monotonically, but the accuracy may bounce around, and then if you stop early on accuracy, you might get like very bad results versus if you stop on other metrics. Yeah. Also, I mentioned already that preprocessing is important, and naive preprocessing is not good enough. And yeah, I think there are like two especially good methods. One is ours, and one is like a quantile transform-based methods. But in general, I think preprocessing should become more important for tabular AutoML, because now we have good neural nets. When we had boosted trees, we didn't really need numerical preprocessing, but now we need it, and we should probably also tune it. So I talked a bit about our benchmarks in the real MLP paper, but there is really a lot that we can do better, and we try to do almost all of it better in Tabarina, which is a large collaborations with people from Amazon, Freiburg, Mannheim, and so on. And one of the main features of Tabarina is that it is a living benchmark, so it's going to be updated, and it has an online leaderboard that you can submit your methods to, and hopefully that also eliminates problems with bad baselines, because you can just reuse our baselines, and our baselines are tuned based on a lot of experience. And when I talk about baselines, I mean boosted trees. We also took quite some effort to try to have more realistic data sets. So unfortunately, out of the like around 1,000 data sets that we looked at, we ended up with only 51, because a lot of them were like not IID, not tabular, or whatever. But I think this makes a difference compared to other benchmarks. We also didn't go for a classification error this time, but for metrics that cover more aspects of the model's performance, like AUC and log loss. And we went for some different aggregation metrics. Our main metric is ELO, which you might know from things like language model arena or chess ratings. What we do better, and one thing that we do better in Tabarina is cross-validation, thanks to having more compute, mainly. So if you want to train a model and you want to avoid overfitting, then you should do cross-validation, which is you split your data into different number of folds, like 5, and you train then 5 models, each of them having a different fold as the validation set. So you get predictions on basically the entire, you get validation predictions on the entire data set, and this gives you more reliable validation scores for things like tuning or ensembling. Also then, when you measure the test performance, you average the predictions of all the models, and you take the test performance of that. And this basically also mimics what is happening in state-of-the-art AutoML tools like AutoGluon. we just take the setting from AutoGluon and use 8-fold inner cross-validation. But so this is for tuning the hyperparameters and early stopping. And then there's also the outer cross-validation, which is to measure the performance of the resulting method, which is this split into training and test data. You can also, of course, do this in folds and repeat this. And here we had a bit of a heated discussion, but we ended up using 3-fold outer cross-validation simply for the reason that per experiment this gives you more test data, so it gives you lower variance and model evaluation. So hopefully you need less folds to get reliable results, and then we rather like repeat those fold results. But we also have a light version for all the practitioners that don't want to use as much compute. So we've heard a lot today about hyperparameter tuning, but actually there's something else you can do. You can try to not find the best model, but try to learn weights to ensemble together different models. And this is works very well. And one of the popular methods to do this is from 2004, a simple greedy algorithm. So you take all the validation set predictions that you got from your inner cross-validation, and you do this greedy algorithm that tries to increment each weight and sees which weight it should increment to reduce the validation loss the most. Yeah, for example, I think we use 40 steps for that. And this is relatively cheap. It has some risk of overfitting. It fits more parameters on the validation set than just an HPO. But I think its main downside is to increase the inference cost, because now you need to do inference on more models. But at least because you did this greedy thing, your weights might still be sparse, so you don't have to do inference on all of the models. Then we might also want to look at portfolios, because we can. So a portfolio is like, you can meta-learn a portfolio, which is a list of model and hyperparameter configs, such that on a new data set, you try all of those, or like the first few of those, and then you use these for hyperparameter and algorithm selection. And basic scheme of a portfolio is we run a dense evaluation, which is one of the trade-offs we have to make in how we run the benchmark. So we use the same set of hyperparameters on all the data sets. And then we can just use a simple greedy method to find a good portfolio. Finally, before showing you the benchmark results, I want to also make this disclosure, basically. Mainly before I was invited as a co-author to this benchmark, I knew that they were going to do this benchmark, and I optimized RealMLP's hyperparameter search space. I used some like custom code with surrogate models. This is not published, so I'm also not going to tell you everything about it, but I would be interested in knowing people's opinions if this is more broadly interesting or not. I also used this later to optimize the search spaces of the boosted tree baselines. So I'm relatively confident that these are very good baselines. And this gave me quite some changes to the actual search space, like some search spaces were just like made larger or changed. I found it also interesting that certain parameters apparently I shouldn't tune, like activation functions. I would have thought, yeah, gives me a lot of diversity, why not tune it? But maybe not. Or the type of numerical embeddings and so on. I also added a few parameters to the tuning scheme, and I added a trick that I found earlier, which is to add a label smoothing schedule, but I won't go into detail there. So these are the main results in Tabarina. For each method, we have 3 variants: default parameters, tuned hyperparameters on like 200 steps of random search, and with this Karana ensembling. And you see it can make quite a difference in like the overall ELO if you do the ensembling or just the tuning. Especially for real MLP, we see like real MLP is here the best method with ensembling, but if you only do the tuning, it's like, I don't know, the sixth best method. So yeah, this makes quite a difference. And then we see here LightGBM is a boosted tree method, cat boost, but tabm is also an MLP method. So really MLPs have caught up with boosted trees according to this new benchmark. And we can also see here is our portfolio across all the methods in this benchmark. And you can see this portfolio is a lot better than all of the methods. And it's also a lot better than the state-of-the-art AutoML method. So we will see actually AutoGluon improve a lot in the next version because it's going to use something like this portfolio. Regarding imputation, what we didn't do in this figure is impute results of foundation models that don't run on all data sets. So here we have tabpfnv2, which is a tabular foundation model that is the state of the art now on smaller data sets. And we have Tabico, which is actually also from me and some co-authors, Jingang and so on. And Tabico is also on its applicable data sets, at least the best method with default parameters. We looked at things like weights in the portfolio, and we found that actually real MLP and modern NCA have like huge weights in the portfolio on average, and we suspect that this is because they overfit more on the validation sets. And if something could be done about this validation set overfitting, then maybe we could get actually better portfolio performances because we have more accurate validation scores. I think some aspects of this benchmark compared to the other benchmarks benefit neural nets, like basically everything that uses ensembling, like cross-validation. We see that cross-validation benefits real MLP more than boosted trees. We see that ensembling benefits it more, but also I know that real MLP is worse on data sets with like classification, AUC, log loss, and we have many of those in the benchmark. We don't have simulated data sets, which is also a good domain for neural nets. And we have a different aggregation, which I think the shifted geometric mean, it favors a lot the models that are good on those deterministic data sets. Finally, I didn't check the time, but I wanted to say a little bit about classification metrics because I learned about this also too late. For the first benchmark. So there is a lot of accuracy type metrics, and if you use these, you maybe should use threshold tuning on like a validation set or calibration set. There is AUC, which like implicitly tunes the thresholds and averages over them kind of. But if you have a model that is good in AUC, you still need to have a separate set on which you can actually tune the threshold that you're using, I think. Yeah, that's, yes. But after, yeah, AUC integrates over thresholds, so it gives you a more complete picture. But afterwards, you need to have some extra data to figure out which threshold you actually need to use in order to optimize your kind of target cost metric, right? Yeah.
Something that measures the discriminatory power of the community.
Yeah.
Make a choice what you want to measure, right?
Yeah. Anyway, what I like now is proper losses, which are losses that in expectation over the labels are minimized by the true distribution, like log loss or like Breyer loss, which is the MSE. The problem with those is you can often improve them by doing post hoc calibration, by like fitting a post hoc transformation G. So ideally you should benchmark methods with such a post hoc transformation, but then you would also need to optimize it because there might be different post hoc transformations that are well suited to those methods. So I guess one advantage of using AUC is that it kind of removes the need for doing this. I think there might be some open AutoML question is as to where you apply this in your cross-validation setup. Do you apply it on individual folds, then again on jointly, after ensembling, and so on? And as another paper and one of our papers argues, if you use post hoc calibration, then you should also early stop on the loss after post hoc calibration. At least if you have enough validation data, there is a bit of an issue. And yeah. A threshold? Do you mean in the AUC case or in the accuracy case? In the accuracy case, you need to threshold your predictions before you compute the metric, right? I mean, implicitly for accuracy, you would threshold on 0.5. But if you use something like balanced accuracy, actually 0.5 might not be the best threshold to threshold on, so you might need to tune it. I also heard from someone that even if you use accuracy, you should maybe tune the threshold. So
I think this is especially bad or weird results for when I've seen it there.
okay.
I actually never figured out why. But it would really improve accuracy by tuning the threshold, which I should be strongly be able to do.
Yeah.
I mean, for the other stuff, I mean, many people just use F1 out of the box with 0.5. That's just ridiculously bad.
And for F1, they need to specify which class is the one class. So I guess they take the rare one, but then this doesn't work for multi-class and yeah.
It's just technically annoying.
Yeah. Okay. So anyway, I hope I've somewhat convinced you that if you do MLPs correctly with a lot of tricks, then you can match or outperform boosted trees, even if you do the benchmark relatively neutrally and correctly. And also we saw in the TAPFN subset results, even on smaller data sets, the neural nets are now better than boosted trees. I think there is more opportunities to improve MLPs, if anyone is interested. Unfortunately, or this is a bit overshadowed right now by the hype of foundation models. So, and we're also working on foundation models, so I'm kind of like torn between those domains. Like we have Tabical, which is a foundation model scaling to larger data sets up to 100,000 samples. And we're continuing to work on that. One thing I found to be a bit missing from the literature is distributional regression. You don't see it in the standard tabular benchmarks, but I find it interesting at least. And for AutoML, I hope you could take away some interesting research question or practical needs, like looking at preprocessing, making algorithms that work for weighted ensembles and not just hyperparameter tuning. There's also stacking, which I didn't talk about, making good meta-learning algorithms that are time-aware and can select efficient configurations and can select good portfolios. And yeah, here are some links to this where we have all the neural network baselines and the benchmarking code. This is our Tabical foundation model with public pre-training code. And this is where you can find some of the post-hoc calibrated loss and so on metrics that we've used in this paper. Thanks.